So, we saw earlier how the acceleration component or the acceleration difference between 2 points on the same rigid body has a normal component and a tangential component. The tangential component is dependent on the angular acceleration, whereas the normal component is only dependent on the angular velocity of the body. So, once you complete your velocity analysis, you actually know all the normal components of accelerations of the various links, okay, because it is the magnitude of the normal component is omega square r, right. So, if I have A, then A, so now let us apply this to the analysis of a 4 bar, and we will just so we will assume the position analysis has been done and the velocity analysis is also been completed. Okay. So, we know all the angles, we know all the angular velocities of the different bodies. Now, let us say I need an angular, I need an acceleration input. So, that could be in the form of a constant angular velocity, which would mean alpha 2 is 0, or I could have a finite, I could have some other alpha 2, a non-zero alpha 2. Okay. So, we can again do our loop closure, we will connect the loop closure and the acceleration diagram. But since we have already done this once for the velocity, I do not want to do it one after the other, we will just do it simultaneously. Okay. So, I have R2 plus R3 equal to R1 plus R4. So, R2 e power I theta 2 plus R3 e power I theta 3 . Differentiating this for the to get the velocities, I got I omega 2 R2 e power I theta 2 plus I omega 4, which basically related the velocities of points A and B on link 3. So, I had velocity of A on 3, B relative to A equals the absolute velocity of B. We differentiate this equation again for acceleration. And we saw we get I alpha 2 minus omega 2 square R2 e power I theta 2 plus I alpha 3 minus omega 3 square R3 e power I theta 3, because if I differentiate each of these terms where alphas are basically d omega by dt equal to I alpha 4 minus omega 4 square R4 e power I theta 4. Okay. Again two equations, one vector equation or two scalar equations. My unknowns are, knowns are all angles, link lengths of course, because you are doing analysis, so you have to know what linkage you are analyzing. All angles, you know alpha, all omegas are known because you have completed the velocity analysis, and alpha 2 is input. So, the only unknowns in these equations are alpha 3 and alpha 4. So, I can solve for those two unknowns. Now, let me solve this. So, I can write this as, I can split this up as A tangential of A on body 3 plus A normal A on body 3, okay, plus this is A tangential B relative to A plus A normal B relative to A. This is A tangential B on body 3, A normal B on body 3, because these two are absolute because they are with respect to the fixed pivot, O2 here, O4 here. That is what it means. When I do not specify the second point, it implies that that is the with respect to a fixed pivot, okay. Velocity and acceleration 0. So, now I can plot these in an acceleration diagram. So, I know, so say I take, let us say O, okay. I have the known acceleration. So, in this equation, okay, let us first do this. In this equation, this one is, I know the magnitude, I know the direction, because alpha 2 is known and I know the direction, it is perpendicular to O2A. The normal component again is completely known because it depends only on omega 2 here, because this is equal to the acceleration of A on body 2. Those 2 points are always coincident. In the case of B with respect to A, the tangential component depends on alpha 3, which is unknown. So, I do not know the magnitude of the tangential component of acceleration of B with respect to A. However, I do know the direction or at least the line of act. So, this, the magnitude is unknown, but the direction is known. In this case, again what is known here? You know the magnitude and the direction, because the normal component, remember, is completely known once you do the velocity analysis. So, you know both, you know omega 3 square from your velocity analysis, you also know the direction is directed from B to A. And here tangential component of this depends on alpha 4, which is unknown. However, you know the line of action of that vector, and in this case again it is completely known because omega 4 is known from the analysis. Okay. So, you see here again I have two unknowns. So, I should be able to solve this vector equation by Only thing is, in the velocity equation we had only 3 vectors to create the polygon. Here we now have 6 to create the polygon, the acceleration polygon. Okay. So, let us start with what we know and what is absolute. So, if this is O, I know the tangential component of this, which would be like this, right, along that direction. So, this is A tangential A3 known. Okay. Normal component would be along from A to O2, that direction, that is also completely known. Okay. So, let us say that is this. Okay. So, I know this point here, completely known, this part. Normal component of B3 relative to A on body 3. So, I can add these vectors in any order, right. So, this is known. So, let me say that I can, that would be this vector in this direction, right, from B to A. This would be the normal component of that. So, I will say that this is the normal component of B3 A3. Okay. This one I know it lies, so I only know the direction. So, let me just do that in a different. So, it is perpendicular to this, the tangential component is perpendicular to this, but I do not know its magnitude. Then here I know these two are absolute accelerations. So, I have let us say A normal B3, okay, and the other component I know, the only thing I know is it is perpendicular to this. Okay, but once I do this now, I get this point which will be, so this to this here, this point is, let us call it A dash, small a dash for the acceleration. Okay, this point here, the whole acceleration of A was completely known, it is this plus this. So, this point is A dash and I added the relative component there. So, this point here will be B dash, the intersection of these two will give me B dash. So, if I draw a vector from O to B dash, that will give me the absolute acceleration of point B. Okay. So, now I know these two components, I know that what is this component here, and that is the direction, because this plus this, right. The direction of this is, what component is this? Tangential component of B with respect to A. Here this is the tangential component of B, the absolute. Srinath, I think I need you to leave. I think if you are distracted, I do not see the point in you being in class. Okay, this is the second time it is happening. It is fine if you choose your phone over being in class, I do not have a problem, but please do it elsewhere. I find it distracting. So this is, so now can we find the, from here I have basically solved this vector equation graphically. So now I can find alpha 3 is A tangential, the magnitude of that by the distance AB, and what would its direction be? So it is like this, it is perpendicular to AB in this direction, which means AB has been rotated, the vector from A to B has been rotated clockwise. So this is clockwise. Okay. What about alpha 4? Alpha 4 is A tangential B3, magnitude of that by O4B, and what is the direction of that? So you have the direction perpendicular to OB like this, which means alpha is counterclockwise. This should be familiar to you. So this is how you solve the, analytically you will just split it into real and imaginary parts. You will have two linear equations in alpha 3 and alpha 4, and you would solve for those unknowns. Graphically you would solve it in this manner. Okay. So although there are 6 terms in the acceleration equation, all the normal components are completely known from the velocity analysis. Okay. So you can solve this equation, but just as we saw for velocity image, right, we saw that I can find, once I know alpha 3, I can basically find the acceleration of any point on this. Okay. So let me just, so here the, just as in the case of the velocity image, you had the velocity triangle similar to the triangle in the linkage, but rotated by 90 degrees in that case and scaled by omega 3. In this case it is a different factor of scaling which you will find and a different angle, but it turns out that acceleration image also applies. So you will find that if I want to find the acceleration of point C, all I need to do is this, reconstruct this triangle, okay, in the acceleration diagram, okay, and that will give me the acceleration of point C. So the triangle in the acceleration diagram will be similar to the triangle in the position diagram. Okay. So here how would I construct the acceleration? Alpha is, it's a different angle. Okay, I'll leave that to you as an exercise to show how the acceleration image is obtained, because if I go into that then I'll just end up doing it anyway. Again, slider crank is fairly straightforward. You just don't have a normal component of acceleration because the slider is going to be moving linearly. So in the case of the slider block, you don't have a normal component. So when you write that equation, you will only end up with the linear acceleration of the slider. That will be the, there is no normal component there. However, I will do the case where for the inverted slider crank. Okay. So let us say because that is where a new term comes in. So, we saw earlier that in this case we had, okay, let's just do it with the loop closure. Okay. So, we have R2 equals R1 plus R4 . Here I am assuming my coordinate system like this. Okay. So, thetas are all measured accordingly. So, here velocity equation, when I look at that, I have R2 I R2 omega 2, R1 is constant, and for this I had I R4 e power I theta 4 plus R4 dot e power I theta 4 when I differentiate this term, because R4 is no longer constant in this case. To close the loop, you are going to have to go, R4 has to change in length as you close the loop each time. So, we saw that this is the velocity of A on body 3, which is equal to the velocity of A on body 4 plus the velocity of A on body 3 relative to A on body 4, a point that is coincident at that particular instant on body 4. Okay. Yes? Okay. So, now we differentiate again to get the acceleration. And we get I alpha 2, in this case minus omega 2 square R2 e power I theta 2 equal to, here I get a similar form. Now, when I differentiate this, now R4 is not constant, R4 is not constant. So, I will get two terms when I differentiate this. What are those two terms? I R4 dot e power I theta 4. Okay. First I keep theta 4 constant, sorry, here, right? Yeah, thank you. I know something looked funny. Thank you. So, I have, okay. So, I alpha 4 R4 e power I theta 4, okay, plus I omega 4 R4 dot e power I theta 4 plus I omega 4 R4 into I omega 4 e power I theta 4. Those are the three terms I get from differentiating this. Yes. Now, from differentiating this term, the second term, I get R4 double dot e power I theta 4. So, this was the slip velocity, if you remember. Okay, this is the slip acceleration plus R4 dot I omega 4 e power I theta 4. This is I alpha 2 is equal to, now if I group the terms, I will get I alpha 4 R4 e power I theta 4, and then I also get a minus omega 4 square, right, this one r 4 e power I theta 4. Grouping this and this, so this is taken care of, this is taken care of. Then I get r 4 double dot e power I theta 4 plus I 2, if I add these two, r 4 dot omega 4 e power I theta 4. Okay. So, now let us look at these terms. This is straightforward, this is tangential component of the acceleration of A on 3 plus the normal component of the acceleration of A on 3, and this is equal to tangential component A on 4 plus normal component of A on body 4. Now, this is something different, these two terms. This is your slip acceleration of A on body 4. Okay, r 4 double dot, along this how are the 2 points moving. So, it is an acceleration of that A 4 relative to A 3 relative to A 4, okay, because that is the slip acceleration, and here this term is called the Coriolis acceleration of A this. So, the Coriolis acceleration appears when you have a rotating slider essentially, okay, right. You have here, you have omega 4 and r 4 dot. They are sliding with respect to a rotating path. Okay. So, when you have both of those, you will have this Coriolis component of acceleration. If you do not do this, I mean you can still write this equation straight away by looking at this, because this would be the acceleration of A on body 3. This is the acceleration of A on body 4, and this is the acceleration of A on body 3 relative to A on body 4. So, from this, directly I could look at this and write this, okay, but I have to remember what the components are. Okay. In this case, it is not the same form for all three accelerations. When the 2 points were on the same rigid body, I had tangential, normal, tangential, normal, tangential, normal. When you have a case like this where you have coincident points, you have to take into account, you have to remember to take into account not just the slip acceleration, but also the Coriolis acceleration. Now, if you see here, the Coriolis acceleration is again completely determined from the velocity analysis, because you know the slip velocity, you know the angular velocity of this. Okay. So, that is completely known after you do the velocity analysis. So, if I look at this equation again, this term, if that is the input, omega, I have omega 2 alpha 2 say. So, this is your input, so it is completely known. direction is perpendicular to the link O to A. This one again normal component completely known from the velocity analysis. In the case of A on body 4, again tangential component I do not know the magnitude because I do not know alpha 4. Alpha 4 is not known, however, I know the direction. It is perpendicular to the link. Normal component completely known. In this case the slip component, what do I know about it? If I look at this term here, I know the direction, it is along the link, but I do not know the magnitude of R4 double dot. So, here R4 double dot is unknown, but I know the direction for this term, and for the Coriolis term again it is completely known because of the velocity analysis. Again 6 terms, 2 unknowns. The 2 unknowns are alpha, what are the 2 unknowns? Alpha 4 and the slip acceleration R4 double dot. Those are the 2 unknowns, and you can solve for them either analytically or graphically. Any questions on this? You will be comfortable solving this graphically? Okay. What is the direction of the Coriolis acceleration? It will depend on the direction of the slip velocity and omega 4, okay, and it will be, so the magnitude will be like this, and so it is basically this velocity vector. See R4 dot e power I theta 4 is your slip velocity vector. So, the slip velocity vector will be rotated 90 degrees in the direction of omega 4. Okay. So, direction of AC will be given by slip velocity vector rotated by 90 degrees in the direction of omega 4. That will be the direction of the Coriolis acceleration. So, you have to be, so plotting that in the graphical will be, it requires some attention when you are doing the graphical analysis. Okay. And this will be along the vector. So, it is sort of the same form. So, this would actually be also perpendicular to this link. The Coriolis acceleration will also, so these are 2 perpendicular components. One is along the link, one is perpendicular to the link. The direction will be determined by the direction of the slip velocity and the direction of omega. Those 2 will determine the direction of the Coriolis acceleration. Okay. So, this is for the cases that we have. Again, this you should be familiar with. This is just a recap of what you already know. So, again this velocity difference method cannot be used for certain types of mechanisms, just as we saw that the, it is obvious, right, if you can't use the velocity difference, you are probably not going to be able to use the acceleration difference for the same kind of mechanism. So, let us look at a case where I think we have time, what is known as a kinematically complex mechanism. So, There are several methods, I am only going to do one of them, because graphical for acceleration is quite tedious. So, most of these can be solved analytically. So, I am just going to do one method, the auxiliary point method for acceleration analysis. Okay. So, here is a case where if 2 is the input, it is a kinematically complex mechanism, because I will know the acceleration of A, but I know nothing about the path curvature of B. Okay. If 6 or 4 is the input, not a problem, I can solve it, right. That is just my 4 bar. I find the acceleration of B after solving the acceleration of this 4 bar loop, and I can then, and A is on a link that is connected to the ground. So, that is straightforward. I can apply the acceleration difference method, but I can't do that if 2 is the input, and using inversion and all that is a little bit more complex when you come to the acceleration analysis. Okay. So, it is not, you can't scale it directly like you do for the velocities, because you saw that every point has 2 components of acceleration. So, it is not as straightforward as the velocity analysis, just inverting the mechanism. So, in this case, the method of acceleration difference or relative acceleration is not feasible, because to apply that you need the radii of curvature of at least 2 points on the of 2 of the motion transfer points. Not known. Two is the input, and you have a ternary floating link. Therefore, this mechanism is kinematically complex. So, let us look at the auxiliary point method. I will just explain the basic principle behind it, and we will do it next class. So, this method again, similar to the auxiliary point method for velocities, can be applied to most mechanisms, whether they are low or high degree of complexity. Most mechanisms can be, and the concept behind that, see, we saw that in the case of velocity, the concept was that along the auxiliary line the component remains the same. In the case of accelerations, it does not remain the same, but they can still be related. So, I will just introduce you to that, and then say this is a point whose acceleration you know. Okay. you have body I and body j. You have some point C on body j for which you are interested in. You essentially want to find how some information about the acceleration of C. So, if you look at, you draw an auxiliary line connecting A and the motion transfer point B. Okay. So, now if you look at this is the acceleration of A along this line 1, auxiliary line 1. Okay. What will be the acceleration of point B along this line? Will it be the same as this? Velocity was easy to visualize. Okay, velocity is going to be the same because the two points are on a rigid body and they can't move towards one another. In the case of acceleration, how is B moving with respect to A? If I look at this, I can write the acceleration of B along this. Remember, the acceleration difference between 2 points has a normal component and a tangential component. So, I can write this as 1 plus BA. Okay. So, this is towards A, the direction is towards A. So, I am just writing it algebraically. Okay. Acceleration of B will be plus a component towards A. Similarly, the acceleration of C will be acceleration of B plus omega j square CB. Okay. And then I can substitute for the acceleration of B. So, this will be acceleration of A CB. Again, all these are known from the velocity analysis, because once you know the velocities, so you can find. So, I know one component. So, let us say now from here I calculate AC along 1. Okay. Then necessarily the head of the acceleration vector has to lie somewhere on this line. Okay, because the other component, 2 perpendicular components. So, this plus some other. So, the head of the acceleration vector of point C will lie somewhere on this line xx. So, if I know one more, if I know the acceleration of another component of the acceleration of C, okay, using, instead of just saying it is equal to, again through some other point, if I can find another component of the acceleration of C, then the perpendicular to that, wherever that intersects this line, is going to give me the location of the head of vector AC. So, that is the auxiliary point method for acceleration. We will solve a problem in the next class, but this is the basic concept behind the auxiliary point method for accelerations. Slightly different from the velocity case, but still quite elegant how they come up with this.